Welcome to AI Research Chat, your daily briefing on the latest in artificial intelligence research. I'm your host, and joining me as always is our resident AI expert. Today is March 9th, 2026, and today we have a great lineup of papers to get through.
Great to be here. Let's dive right in.
Let's start with benchmarks, specifically the problem of AI agents being tested against environments that never change. What's the issue there?
So the way most agent benchmarks work today is you freeze everything, the APIs, the database schemas, the available tools, and you test the agent against that fixed snapshot of the world, which sounds fine until you remember that the real world does not freeze. APIs get updated, fields get deprecated, new endpoints appear. When you test against a static environment, you're essentially measuring whether the agent has memorized that particular state of the world.
So the benchmark scores could be completely misleading.
Exactly. A team at UC Berkeley and Yahoo Research built something called ProEvolve to address this. They represent the whole environment as a graph: data nodes, tool nodes, schema relationships, and then they express changes as graph transformations. Adding an API endpoint is a transformation. Deprecating a field is a transformation. And because those transformations are explicit and programmatic, you can chain them together to generate entirely new environment variants automatically.
How many variants are we talking?
They took a single seed environment and generated 200 distinct variants and 3,000 task sandboxes from those. And when they ran agents across that suite, they saw meaningful variance in performance across evolved environments, variants that the static benchmark would have completely hidden.
I would not have guessed that.
The implication is pretty direct for anyone building or evaluating agents. If your benchmark never changes, your score measures memorization, not adaptability. That's a methodological problem the whole field needs to reckon with.
Speaking of benchmarks having hidden flaws, there's a paper about fact-checking AI-generated research reports, and apparently even experts struggle with it.
This one is striking. The paper is about what they call deep research reports, long-form documents produced by search-augmented AI agents. And the question is, can you build a benchmark to test whether a fact-checker can correctly label the claims in those reports? So you bring in PhD-level domain specialists, and you ask them to label a set of verifiable claims. Their accuracy on the hidden test set is 60.8%.
Wait, really?
PhD experts, one shot, 60.8%, which tells you two things. One, labeling fine-grained factual claims in complex AI-generated research is genuinely hard. Two, any benchmark built from one-shot expert labels is going to be unreliable. The insight in this paper is that experts are much better as auditors than as labelers. So instead of one-shot labeling, you run what they call audit then score. When a verifier disagrees with a label, it submits evidence, an auditor adjudicates, and the label can actually change before scoring happens.
So the benchmark evolves as you test it.
Right. After 4 rounds of that protocol, expert accuracy on the same test set rises to 90.9%. The benchmark and the verifier improve together. For developers building fact-checking pipelines on top of AI-generated content, this is the right infrastructure model: versioned, auditable, contestable labels rather than a frozen ground truth.
Okay, let's shift to safety. There are 2 papers today that look inside LLMs at the level of attention heads and neural geometry, which sounds abstract but apparently has very concrete consequences.
Both papers are about jailbreaks, but they approach the problem from different angles. The first one, Saha, starts from an empirical finding. Deeper attention layers are more vulnerable to jailbreak attacks than shallow ones. Alignment training installs safety circuits early in the network, but those circuits are not as well reinforced deeper in. So the attack finds the most safety-critical attention head in the deepest vulnerable layer and applies minimal perturbation to it, just enough to unlock unsafe outputs, small enough to stay under detection thresholds. That 14% improvement in attack success rate over state-of-the-art baselines comes entirely from targeting this underdefended part of the model.
That's wild. The defenses are looking in the wrong place.
And the second paper goes even deeper conceptually. It proposes something called the disentangled safety hypothesis. The idea is that safety in an LLM is not one thing, it's 2 separate mechanisms operating in distinct neural subspaces. One subspace handles recognition. Does the model detect that this content is harmful? The other handles execution. Does the model actually refuse? In early layers, these signals are entangled, but in deeper layers, they become structurally independent.
So the model can know something is harmful and still not refuse?
That's the knowing without acting state they demonstrate. And the practical implication is that if you can find and selectively suppress just the refusal axis without touching the recognition axis, the model keeps detecting the harm but stops acting on that detection. For defenders, this means safety evaluations that only probe prompt-level inputs may be completely blind to this class of attack. Different model families also have different vulnerabilities here. Llama uses localized safety representations, Quen uses distributed ones, so the attack surface looks different for each.
Right.
It's a useful reminder that the model passed our red team eval is not the same as the model is robust to all attacks.
Let's talk about chain of thought monitoring, because this is one where the finding is actually reassuring, but with a big asterisk.
Yes. The premise is, if a model reasons step by step before answering, can safety teams watch those reasoning steps to catch bad behavior before it reaches the output? It only works if the model can't hide what it's actually thinking in the chain of thought. So this paper measures directly whether models can control what they write in their chain of thought. And the numbers are striking. Claude Sonnet 4.5 controls its chain of thought only 2.7% of the time, but it controls its final output 61.9% of the time.
Wow, that's a lot.
The gap is enormous, and it means current models are genuinely unable to deceive chain-of-thought monitors, not because they're honest, but because they structurally can't suppress what they verbalize in their reasoning. COT controllability also decreases with more RL training and more test time compute. So as models get more capable in ways we usually celebrate, their reasoning becomes harder for them to control, which is actually a safety bonus, at least for now.
What's the caveat?
Nobody understands why this is the case. The mechanism is unknown, and since frontier capabilities are increasing fast, we need to actively track whether COT controllability changes his model's scale, because if it suddenly goes up, the safety assurance for monitoring collapses.
There's a very different paper today about TikTok and EU regulations protecting minors from targeted advertising.
This one is a sharp piece of empirical work. The EU's Digital Services Act has a provision, Article 28.2, that prohibits profiling-based advertising to minors, and TikTok formally complies with it. Minors don't get profiled formal advertisements. But here's the gap. The DSA's definition of advertisement is narrow. It only covers content that explicitly identifies itself as an ad.
Influencer content, brand deals, native promotions, none of that counts?
None of it. And the audit found that disclosed and undisclosed commercial content, sponsored posts, brand partnerships, unlabeled promotions, is profiled to minors 5 to 8 times more intensely than formal advertising to adults. The strongest profiling of all is in undisclosed commercial content, the stuff creators fail to label and the platform doesn't catch. So the regulation achieved formal compliance while leaving the most effective commercial influence completely unprotected.
That is a loophole you could drive a truck through.
The recommendation is to define advertisement functionally by commercial intent, rather than by disclosure format, because right now, shifting the same influence from a regulated channel to an unregulated one is a complete compliance bypass.
Last one, and this feels foundational. There's a paper about recursive self-improvement and the risk of models drifting out of alignment as they improve themselves over multiple iterations.
SAHOO builds a monitoring framework specifically for this problem. When a model revises its own outputs across multiple cycles, small alignment shifts can compound. Their goal drift index combines semantic, lexical, structural, and distributional signals into a single learned detector that quantifies how far behavior has moved from the aligned baseline.
Does it actually work?
Across 189 tasks, code generation, math reasoning, truthfulness, they get 18% improvement in code and 16.8% in reasoning while keeping constraint violations low. But the key finding is the capability alignment frontier they map. Early improvement cycles are efficient and cheap on alignment. Later cycles carry rising alignment costs, meaning unconstrained long-horizon self-improvement is risky even when each individual step looks safe.
So it's not about any one step going wrong. It's the accumulation.
Exactly, and that's actually the thread running through a lot of today's papers. Static evaluations miss dynamic drift. One-shot labels miss the revision process. Prompt-level defenses miss deeper layer attacks. The biggest theme today is that safety and evaluation both need to become continuous, evolving processes, not point-in-time checkboxes.
And building the infrastructure to make that possible, auditable benchmarks, drift monitors, cryptographic guardrails, that's where the real work is right now.
That's where practitioners should be looking. The problems are real, the tooling is nascent, and the gap between the two is where the most important engineering is happening.